Black holes can be smaller than an atom, older than galaxies, and possibly more numerous than all the stars you can see in the night sky combined. And if even half of that is true, our picture of the universe is wrong in ways that are hard to overstate. For a century, black holes were the monsters at the end of stellar life. Massive stars collapse, gravity wins, and you get a dark, dense point from which not even light can escape. Clean, predictable, rare. Primordial black holes rip that comfort away. These are black holes that could have formed not from dying stars, but from the raw chaos of the first fractions of a second after the Big Bang, when the universe was denser than an atomic nucleus and expanding faster than any explosion we can imagine. In that era, tiny fluctuations in density, quantum jitters, magnified by cosmic inflation, might have been enough to crush pockets of space into black holes of every size, long before the first star ever shone. This idea changes what matter even means. In physics, we split the universe into visible matter, atoms, stars, gas, and dark matter, the invisible mass whose gravity sculpts galaxies, but which refuses to interact with light or normal particles. For decades, dark matter has mostly meant new particle we haven't discovered yet. WIMPs, axions, sterile neutrinos. Elegant, but hypothetical. Primordial black holes offer a brutally simple alternative. Maybe dark matter isn't a new kind of particle at all. Maybe it's just gravity itself, locked into countless ancient black holes drifting through space. If even a fraction of dark matter is made of these relics, then the universe is not mostly made of exotic particles. It is mostly made of collapsed space-time, fossils from the first heartbeat of the cosmos. That would mean the universe is a black hole ecosystem. Think about the Milky Way. We know there's a supermassive black hole at its center, about 4 million times the mass of the Sun. We know stellar mass black holes pepper the disk, born from dead stars. Now add a hidden population of primordial black holes, some as small as mountains, some as massive as planets, orbiting quietly in the galactic halo. Suddenly, the galaxy isn't just stars orbiting a central monster. It's a gravitational coral reef. Big black holes, small black holes, and maybe even black hole families where tiny ones orbit larger ones, like moons around planets. Every time two of them spiral together and merge, they send out a burst of gravitational waves, ripples in space-time, that observatories like LIGO and Virgo can detect. And intriguingly, some of the black holes we've already seen through gravitational waves are in mass ranges that are awkward to explain with normal stellar evolution, but natural for primordial ones. This is where tiny black holes start masquerading as exoplanets. When we detect a planet around another star, we often rely on subtle tricks. A tiny dimming when the planet passes in front of the star, or a slight wobble in the star's motion due to the planet's gravity. But there's another method, microlensing. When a compact object passes in front of a background star, its gravity bends and focuses the star's light, making it briefly brighter. Microlensing doesn't care what the foreground object is made of. Rock, gas, or pure gravity wrapped in an event horizon, the light curve can look almost the same. So some of the rogue planets we've detected, drifting without a star, could instead be primordial black holes with roughly planetary mass. If that's true, then our catalogues of lonely worlds might secretly be a census of ancient black holes, misfouled because we assumed planets were the only option. Now stretch this black hole thinking to its wildest scale. What if our entire universe is inside a black hole? This sounds like science fiction, but it grows from serious general relativity. When a massive star collapses, an external observer sees a black hole form with an event horizon, a boundary beyond which information cannot return. Inside, the equations don't just describe a point of infinite density. In some solutions, the interior can be interpreted as its own expanding space-time region. To someone inside, it could look like a universe that began in a hot, dense state and has been expanding ever since, which is exactly how our universe behaves. In this black hole universe hypothesis, what we call the Big Bang, might be the birth of our region inside the event horizon of a black hole in some larger parent universe. If that's even approximately right, the implications are dizzying. First, it reframes the Big Bang. Instead of a singular, absolute beginning from nothing, our cosmic origin could be a transition, a bounce from collapse in a higher-level universe to expansion in ours. Second, it suggests that the constants of nature, the strength of gravity, the charge of the electron, the mass of the Higgs boson, might be like genetic traits. Universes whose physics naturally produce lots of black holes would in turn spawn more baby universes inside those holes. This idea, called cosmological natural selection, hints at a kind of Darwinian process on a cosmic scale. Universes that are good at making black holes become more common in the multiverse. And third, it means that studying black holes isn't just about understanding extreme objects. It might be the only way to glimpse the rules of a reality that extends beyond our own cosmic horizon. All of this forces cosmology to grow up. If primordial black holes exist in large numbers, we need new surveys, new gravitational wave detectors, and new microlensing campaigns designed not just to find planets and stars, but to weigh the invisible. If some exoplanet candidates turn out to be tiny black holes, we'll need to rethink how we classify worlds and how we interpret the architecture of planetary systems. And if our universe really could be the interior of a black hole, then questions we once filed under philosophy, why these laws of physics, why this amount of entropy, become testable, at least indirectly, through the statistics of black holes and the structure of space-time. Because in the end, every black hole we find, from the microscopic to the supermassive, might be more than just an endpoint of gravity. It might be a clue that the universe we see is only a small, curved patch of something far larger and stranger, waiting just beyond the next horizon.